Yeah, thanks for having me. I'm the last-minute replacement, so apologies in advance for being unprepared. This is me on Twitter, so you can publicly show my failures. Let's just do some live coding, have some fun. Normally I talk about software design and modeling and DDD and all that stuff, but my pandemic hobby was writing a Haskell-style, pure functional parser combinator, wait for it, in PHP. So let's do that, and may the gods of demos have mercy on our souls. So help me out if I do stupid stuff, right? What's a parser? Let's start there. Who wants to take a guess? Well, you don't need to guess. You know what a parser is, but how would you define it? Any brave souls? What does it do? So you're all very shy still, but a parser takes an input and returns a more structured version of that, right? Typically we'll parse strings, but you can parse anything really. You could take any data structure and parse it into some more relevant data structure. So let's write a very simple parser that can parse the letter A. So we'll take some inputs. Okay, this is a bit inconvenient. If we have something to make this higher, that would be easier, but I'll try to. It's hard on my hands, but so we get an input. Let's call this result. The substring of that input, the first letter. Oh, yeah. And now we need to verify if. Well, actually, let's just return it first. So we can test that. So this is this readable in the back, by the way? Let's write a simple test. Is that my typo? Oh, return R, sorry. Yes, let's write a test. Well, not a proper test, but just a quick assertion. So our A parser applied to the input ABC should return the character A. Not super useful, but it's a start. Let's run this. Okay, so this is working correctly. But of course, now if I run this on some other input that doesn't start with the letter A, we get a failure of the assertion, as expected. So I'm going to refine our definition of parser now, right? A parser is something that takes an input and either returns a more structured input or it fails, right? So now we'll add some failure to this. If our result equals the letter A, yeah, actually we didn't even test that, so it was a very bad parser, right? But so now we will, we have this code here, so let's just do it like this. Else, let's just throw something, right? Expected A. So let's first see if our original test is still working. No, I don't want to dictate. Syntax, yes, sorry. Yes, okay, so this is working. And now if we do something else, it throws expected A. So now we have a smarter parser, right, that can actually deal with failure. This isn't pure functional programming because an exception is sort of a side effect, right? It's not, so we actually need to express the error in the return type instead, as opposed to just throwing it, which actually also allows us to do more with that, with that error. But before we do that, we are losing information right now, which is if we had this, we have the first letter, but we lost the rest of the string, right? So we need to somehow store it as well. So what we can do actually is, actually I'll rename this one to parsed for clarity. And what we also want is the remainder of the string so that we can use it later, of course. So we can use the same code. This is all going to be not very like clean code or whatever, but so this will take the rest of the string, and now we can return both. The simplest thing we can do for now is just an array. And update our test, of course. We want this to be BC. And there we go. Agreed? So we're going to refine our definition of parser again, right? A parser is now, I'll write it down, parser is a function that takes some input and returns either, I'll add some brackets, some structured value and the remainder, or an error. Agreed? So whenever I say parser, you think a function that takes some inputs and returns either a value or a structured value and a remainder, or an error. So we have an abstraction now, right? And this bit here, so actually let's do it like this, is a function that takes some input and returns. This whole bit, let's make another abstraction here. Let's call this result. And I did prepare a little bit just before, which is writing a class that represents this whole data structure. Right? So the result is the parsed value and the remainder, or it's the error. And I added some convenience functions like is success, is fail, and some constructors basically. Make sense? So now when I say a result, you can think either the structured value and the remainder or the error. So actually let's, we have it right. Okay, so now let's update this function to actually use that result class. So I'm going to change this to succeed with the parsed value. So this succeed function will construct our result, else it will return the fail, I think I called it, yes. Expected A. Of course, we need to update the test. So we can now, actually, let's call this one, introduce a variable, the whole thing, result. And now we can test our result, right? So like this is success. And we can test, for example, the parsed value, which we still expect to be A, and our remainder to be BC. All good. Yes? You still with me? We can actually write a test for parsed. Yeah, okay. We can write a test for the error case as well if we're trying to run the A parser. So the A parser is a parser that parses A, obviously, on a different string. Now we can assert, let's just do it like this. Assert a failure. And yeah, there is no, we could assert the error message as well. I'm not even sure if I have that. Yeah, error. So we can close this again. Let's test on our, make a bit of space. So our errors should be expected A. And this is all good, so we're green. Yes? This is a very boring, uninteresting, useless parser. Let's make it a little bit more generic, right? So now, if I wanted to write a parser that can parse the letter B, I could either copy this code. Let's not do that. But let's add an abstraction, right? Maybe your first instinct here is to say, we can pass the character as an argument. But now this function is not a parser anymore. Why not? A parser is a function that takes some input and returns a result. This is taking two arguments. It's not a parser in our definition, right? In our parser design here. So instead of that, we're going to make a function that generates an A parser, right? And that uses that input. So let's call it character. Character is a function that takes some character as input and that returns a new function. And this function is the parser, right? So this function takes some inputs and returns a result. And now I'm just going to copy-paste all this code and make it more general. So it parses the first character, takes the remainder. Now it checks, instead of A, it just checks if it's equal to our character here. Actually, we'll need to put that in the use statement. That's a PHP thing, you can ignore it. And then, of course, our error message, we can also make it a bit more precise now. So now, what did I miss? Yes. Let's just do that here. So we have, let's first make the parser, and the parser is the character function. We call it on A. So this does not produce a result, right? This produces a parser, which is a function that takes an input and returns a result. So, and now we can use the parser the same way that we used this here. So I can now, for example, say result is our parse function applied to some input, ABC. And now we can assert that result again. Actually, this is going to be the same stuff here. So let's just copy that. And here we go, right? So we made a function that makes a parser. And now we have a more generic. So this function is a parser combinator. A combinator in functional programming is a function that creates functions or that uses functions to combine them into other functions or a mix of those things. Right? So this is our first combinator. And now, of course, I can prove that this also works for other characters. So we could basically do this, for example, and the remainder here is still PC, so this code still works. Yes? You with me? All right, let's make it more interesting. We want to do, for example, parse more than just the first letter, of course. So let's parse the first letter and the second letter, and we want them to be A and B. So let's just do this here so we don't have to type it over and over again. We're going to need a function. We could make a function that checks the first two letters, of course, right? But then we're doing something very specific again, and we want to make more generic reusable code. So let's write a function. Let's call it sequence, for example. And sequence is not a parser, but it's a parser combinator. So it's combining other functions to make a function. So we want sequence to create a parser for us. It's not a parser, but it creates a parser. And how does it make one? Well, it starts with the first parser and the second parser. And in fact, maybe to help explain this, I should already show how we're going to use that. So sequence takes a character parser for A and the character parser for B. And that whole thing now creates our parser. So if we're going to want to use that, we're going to, actually let's apply it on our result. So result, which is again our result data structure, is the output of parse applied on an input. Why is this complaining? Oh, because it's broken. It's not finished, of course. But we expect our result, well, to succeed and to have as the parsed, did I call it parsed? Yeah. So the parsed value of this is going to be B, and I'll explain why in a bit. But we're just doing sequence. We're saying the second parse, the value we're trying to parse with the second parser is what we're interested in. We're saying we're looking for something where parser 1 succeeds and then parser 2 succeeds, and we want the parsed value of parser 2. So this sequence is a parser combinator, so it will have to return a parser, which is a function that takes an input and returns a parse result. Function takes an input, returns a parse result. How does it work? Well, let's first get the results of the first parser. So the first parser is P1. We're going to apply that to our inputs. That gives us a result. And then we're going to check if it succeeds. So if P1 is success, I'm used to having types, and here I don't have them properly, so it's not giving me type hints, but sorry, R1, yes. Is success, then we can continue. Else, we're just going to return the result of parser 1, because if it's a failure, we're basically failing early, right? We're saying if the first parser here is already failing, we just return the result, which is an error. And then, of course, here, if it does succeed, we want to apply the second parser to the remainder of the first result, right? So result 2 is parser 2 applied to result 1's remainder. And we don't need to do an if, because it's already embedded in the parser, right? If parser 2 fails, then this is a failure. If it succeeds, it's a success, so we can actually just return the result of parser 2, which is R2. We need to include these things. Oh. Still with me? Yeah? Excellent, smart audience, I love it. Okay, so it's working, right? So here, we're testing the input, we're running sequence, or we're creating a parser using these functions, which also create parsers. We're combining them, and then we use that new parser that we created on our ABC input, which now shows that our result is in fact a B. It means that we found an A first, and then we found a B. If we didn't find an A first, like this, then we never get to the second parser. It's complaining that, parsed. It's complaining here, actually I should have, I can now assert on the error, right? Or I'll just dump the error. So results, error, so we can see it. Here, yeah. So our error is expected A. So the parser failed early because the first character was not an A, and it couldn't even get to the B, even though the B is there. Agreed? Of course, now we lost some information, which is the A, right? But the point of this sequence parser is not to capture everything. For example, when is this useful? If we want something like this, we could now if we want to capture a B that is surrounded by braces, right? So now we could do this. Well, sequence only accepts one parameter or 2 parameters for now, so we cannot do the third one, the second brace yet. But here, this should now parse. Yeah, parse inputs. That's what I should do here. And now we have the B, and the remainder is, well, here going to be this. Actually, what's wrong? Parsed B. So input, the first character, we parse it. Oh, we're doing weird things here. I think like this. Yes. So you see how we can sort of ignore information in the string that we don't need, but still figure out where it is. You're doing this with regular expressions usually, probably, right? But this is sort of a very natural way of starting to describe things. We could do something where we do keep the characters. For example, an append. Let's actually do, let's write that. Let's actually write our test first. So we want to parse this. We'll ignore the last brace for now because we don't have code for it yet. But now I want a parser that allows me to No, I'm making it too complex. Let's keep it simpler. We want this. We want a parser append which checks for A and B, and we parse the input. We expect the parsed thing now to be the 2 characters, and success and the remainder. Yeah, we know that this works, so let's just ignore some of this stuff. Get rid of it here. So now we need the append combinator. It's again a combinator. It's pretty similar to our, actually maybe I should even copy it. Or am I now challenging the gods of demos too much? Can somebody sacrifice a goat or something? So what we're doing now is we're actually going to keep using the first result and combine it, append it with the second result, right? So instead of returning the second result now, we actually need to make a new one. So if, now we have to test this, right? If our second parser is a success, then we need to make a new result. So let's call that succeed with the value, the parsed value of the first result. I'm doing string concatenation. We'll just, like, for convenience, assume that everything is strings, although, of course, in reality, this might be more advanced. But we'll get the, yeah, that's string concatenation. Get the parsed result of the second parser, return that as our succeed, and then we still need our remainder, which is still the remainder of the second result. And if it's not a success, the second parser, we can still return the result of the second parser because it's just a failure, right? So what did I miss? I needed to rename this one. I kept the other one, right? Yes, okay. So this one is append. And now we can do stuff like this, I hope. Nope. 39, yes, thank you. You're very observant. Perfect. You get a cookie. All right, so still with me? We have append, which sort of works like sequence, but instead of ignoring the first parse thing, it appends it to the second one. What else do we want to do? Oh yeah, let's do something fun. We want to parse anything that either starts with an A, so let's do it like this, X, Y, or that starts with a B. Yeah? Let's call that, well, or is probably like a reserved keyword, so let's call it either. Right? So what is either? It's a parser combinator. So it's a function. Oh, not this. Why is that not even the first choice? It's a function that takes a parser and another parser, and it returns a new parser, so a function that takes an input that will return a result. It will try the parser on the first parser on the input, so parser 1 applied to input. Yeah, I could have copied that stuff, but so if it succeeds, let's just take all this stuff again. So if our first parser succeeds, we will just return the result, right? It's actually easier here. We just return. No, wait. Yeah, if it succeeds, we return the result of the first parser. If it fails, this is where we do the other work now. If it fails, we want to try again with the second parser, right? So we ignore the failure. We try again with the second parser. So if parser 1 failed, we're going to have the result of parser 2, which we apply to the input, and now we test it. Actually, we don't need to test it, because whether it succeeds or fails, that's the output we want. So we could just actually return this straight away. We need to do some imports. Okay. So let's just reuse this. We called it, did I call it either? Yes. Either character A or B. So let's do it like this. We can now test on, I was going to use X, Y, Z, right? So parsed is A. We could test for remainder, but I'm pretty sure it works, so let's ignore that. And now we'll do a second test for the second possibility, which is that it starts with a B, which will parse our B and succeed. And we could, of course, also test for something else where we have maybe X, Y, Z as the input. So, of course, we expect this to fail. Something like this. Who thinks this will work? Nobody? Oh, so little trust in me. And it works. You're all wrong. All right, we have a little bit of time left. And of course, the whole point of this now is we can start doing more advanced stuff, right? There's a lot more of these combinators. Like if you use, typically you wouldn't write all this stuff from scratch. You would use a parser combinator library that has all these basic building blocks, and then you can use that to build your own parsers. I'm still not really showing how this becomes valuable, right? Because I promised you structured data. This is not very structured yet. I'll show you one combinator that will help us to do that. Let's make a quick, I think we have time for it. Let's make a very quick AST. Let's call this, let's just call it element. Let's say that, yeah, let's maybe have a, I'll even do this, value. Let's have number is extends element. So number is a type of element. And yeah, we don't even need code, I think. And let's call it sign, extends element. So we're going to actually parse a string now into an AST, into an abstract syntax tree, into basically a data structure that is a bit more useful. We still lack a lot of useful tools to do it properly, but let's just see how far we can get this. The function we're still missing, the important one here is map. And what map does is it takes an existing parser. So it's a function, it's again a parser combinator, right? So it takes a parser and a map function, and just like mapping something over a list, we will map a function over the result of the parser if it succeeds. Make sense? So we're passing this parser. If it succeeds, we'll map the value, the parsed value, into something else. If it fails, we just have a failure. So we return a function that is a parser, therefore takes an input. I don't know why, oh, it doesn't matter. What am I doing? Oh no, this is why it's wrong, of course. So it takes an input. It will try our parser on our inputs. So we've been doing this a couple of times now. I've forgotten to include this a couple of times now. Okay. If our result is success, then, well, what I just said, right? We will basically make a new result, a successful one, where we take the value, well, we take the mapping function. So this is just any sort of function that takes one argument and returns something different. So it takes the mapping function that we had earlier, apply it to the parsed value, and that's it, right? And we also need to return our remainder from the parser. So remainder like this. Else we just return our result, which is a failure. Make sense? So let's apply this on something very simple now. So our parse function is the map function applied to the character parser for, well, let's do it like this. And we will map that. What will we map that to? Well, it's a string, but we actually want to use the numbers as numbers, right? So let's map the string to an integer. No, actually, let's map it to, we had our AST. Let's just map it to the AST. So we need a function. Well, I think we should just use the short notation if I remember how that works in PHP. So it takes the value and returns the new number of that value. All right. What am I doing wrong? Why is this complaining? Let's see, I don't know. I need a constructor for number, yes. Thank you. Can't it generate that? There we go. All right. So now let's test this. So we want to assert that if we use our parse here on the input, actually let's store the results separately. If we use our parse on the input 1, we assert that the result is an instance of number, and we can also dump it if we like, but let's just trust that this works. Okay, so let's see if this, where my map, yes, I still make that mistake. What else did I assert? It's not an instance of number, because of course I did use this. Let's call it to int, or to, I'm sorry? Yes, R is not, yes, so it's actually R, our parsed is our instance of number. Thank you. We're not there yet, and because we still have some other crap here probably, let's get rid of it. Do I have more? No, here, close some stuff. Yeah, let's get rid of this and just focus on that, and now we're good. Okay, so now we have a function to element that takes a value and creates this element type, which is here is number, and we can map the result of a character parser to an element. So what we can do now, for example, is, well, actually our AST, does it support? Yeah, it's not clever enough for AST. To actually, what I wanted to do is be able to parse something like this. Of course, to do this properly, right? And I'll just explain it in the hopes that it will be enough for you to see what that is. But we could write a digit parser, for example, that finds in a string, finds the numbers, checks if they are indeed digits, and then returns a successful result. And then we could use map to turn that string, because it's still a string of numbers, into a number in our ASD, right, in our data format. And then we could do the same where we try to find signs like this, or symbols, parse them, make a special parser for that called symbol or something, put that in our AST. And our AST actually, what it doesn't support yet is proper like tree mechanism, right? But then eventually we would build up a data structure, a nested data structure that represents a more structured version of this string, right? Because now instead of just a string, we have elements that are either signs or numbers, and we could then, for example, work through that AST to actually calculate a result. I will show you some stuff before we go. So this is the library that a friend and me wrote during the pandemic. It's actually working. It's not very fast yet because PHP is not really built for pure functional programming. But here, for example, you see already one example. This is between this character and this character. We have at least one alphabetic character. So this can now, at least one, of course, means there should be more than, or at least one letter in here. So now we can parse the fact that there is a word between brackets here. I think maybe it's easier to show it here somewhere. Yes. This is a JSON parser. This is the structure of a JSON parser. It's an element, and an element can be either an object, an array, or a value. And then an object consists of the curly braces, some white space maybe, optional white space, followed by a string, followed by optional white space, followed by the colon and a value. And then it's repetitive, right? So it can either end here, or it can have a comma and do this again. You know how JSON works, right? And then the value can be an element again. So a value can be either an object or an array or one of these other things, right? So it's a recursive structure. So here I have, using Parsica written in PHP, we have the whole JSON parser. It is 230 lines, more or less, with a lot of comments and type annotations. But so how does it work? Well, JSON is optional white space, followed by a sequence of JSON elements. What is a JSON element? So this parser here. An element is recursive. So we have in this library a way to parse recursively. And then you recurse on any, this is not a parser combinator, of course. The any parser combinator takes a number of parsers and just has, it's like our either function that we created earlier, but it can do more than two arguments. So it can take any number of arguments, and the first one that succeeds wins. So if the first thing we find is an object, then we go into this parser. If not, we try this one until the end, right? And then an object was an object. Well, it's between curly braces. There are members separated by commas. What is a member? Well, a member is the combination of a string literal, the character, the colon, and another JSON element, which again is recursive, of course. So you see how actually in like the structure of our parser encodes, mimics the structure of how this thing is actually constructed, right? So it's a very it becomes a very natural way of describing the structure you're parsing, and then on top of that, you can sort of map it directly into the data structures you want. Here, of course, like typically how you use an existing JSON parser is to first you have a generic JSON parser parsing it and then returning you an object structure, and then you're actually doing work with that object structure, right? You could turn that object structure into a more usable structure for yourself. So that is a second parsing phase, right, that you are doing, that is application specific. With this code, you can actually just extend this existing JSON parser with things like maps to, in one step, parse from a raw string into your application-specific data structure, all using this sort of very elegant, fluent language. This library even allows you to parse expressions. There should be some examples here, maybe, or maybe in tests. So this here, for example, is a recursive Boolean expression parser. So it can do this stuff and turn it into our AST data structure, right? Which we then can use, of course, for other things. Here, for example, this is what I was trying to get at, but Well, this is the example, but not the test. But here we are basically describing a calculator. So it can take unary operators well, I'm already 5 minutes over, so I should probably stop. But it can take strings like this and not just parse them, but in the same step, actually calculate them, because it's just mapping and other combinators to turn it into something useful in our application. So it's, a very elegant and fun way to do parsing, basically. Thanks for listening. I'm Mathias Verraes.